Okay, we saw in a previous section that the powers of a regular transition matrix always approach a limiting matrix. Now we're going to talk now about something called an absorbing Markov chain. Now both the regular and absorbing Markov chain have an important similarity. The powers of the transition matrix for an absorbing Markov chain also approach a limiting matrix. But let's review some concepts first. A state in an absorbing Markov chain is called an absorbing state if once the state is entered, it's impossible to leave. Consider this transition matrix. Now notice here that from state A, you can only go to state A. So you can never go from state A to state B or state C. It's impossible. Once state A is entered, we cannot leave it. Our only option is to return to state A. So A is an absorbing state. Now B is not an absorbing state. Since it's possible to leave B, you got a 50% chance of going to A. So you can go from A or you can go from B to A or B, and C you can go from C to B or C. So it is possible to leave state B and leave state C, but not possible to leave state A. So A is an absorbing state, but B and C are not absorbing states. Okay, here's an interesting transition matrix. So to go from state A, you can only go to state C. So therefore, it's possible to leave state A and go to another state. If you look at state C, it's possible to leave state C and go to state A. So A and C are not absorbing states. But B is an absorbing state because the only place you can go from B is to go to state B. Now, which states are absorbing states here? Well, since you can leave A and go to B, then A is not an absorbing state. You can leave B and go to A, so B is not an absorbing state. But C, the only place you can go is back to C. So in this case, C is the only absorbing state. Now, let's talk about that. A state in a Markov chain is absorbing if and only if the row of the transition matrix corresponds to the state has a 1 on the main diagonal and zeros everywhere else. Okay, so basically you saw here that for this row C, there's a 1 on the main diagonal, and then there's zeros everywhere else in that row. So C is actually an absorbing state. Up here for A, let's see, not A, B. B is an absorbing state because it has a 1 on the main diagonal, which would be, this, and then has zeros everywhere else in the row. So therefore, that's how you tell if you have an absorbing state. Now, the presence of an absorbing state does not guarantee that the powers of the matrix approach a limiting matrix, nor that the state matrices in the chain approach a stationary matrix. So keep that in mind. Now, if we were to take the matrix P below, okay, what I meant to say is if you look up here at P, at this matrix, and if you were to raise this to the second power, you actually will get this matrix where the diagonals go this way. And then if you multiply it by P again to get P to the third power, you get this matrix. So that just returns back to what it started at for the P matrix. So actually this matrix just oscillates between the two transition matrices. Okay, so this will not approach a limiting state because it just bounces back and forth as we multiply. Now, a Markov chain is an absorbing chain if there's at least one absorbing state and it is possible to go from each non-absorbing state to at least one absorbing state in a finite number of steps. Now that's a mouthful, but let's take a look. Now, right here, we have two matrices, P and Q. Alright, let's consider the P diagram. So I drew a diagram here for you, and you can see that you can go from A to A with a 100% chance, and that's pretty much the only place you can go from A. From B, you got a 50% chance to return to B, and you got a 50% chance to go to A. From C, you got a 50% chance to go to B, and a 50% chance to return to C. And I'm getting this from the transition matrix. Now, A is an absorbing state because you can't leave that state. So the first condition is met here because there's at least one absorbing state. To meet the second condition, we must show that it is possible to go from non-absorbing states in B and C to an absorbing state in a finite number of steps. This is pretty easy to show. It is possible to go from state B to state A in one step. So I can go from state B to state A in one step, and I can go from state B to state C in two steps. So let's see, B to C. Okay, I'm sorry, state B to state C to state A in two steps. So I can go from, let's see, from state B to state C to state A. So state B, I think I meant C to B to A. I can go from state C to state B to state A in two steps. Okay, because you can see I go from C to B, and then I can go from B to A in two steps. So basically, we've satisfied the two conditions. There's at least one absorbing state, which was A, and it's possible to go from each non-absorbing state to at least one absorbing state in a finite number of steps. So I can go from the non-absorbing state B to A easily, and I can go from the non-absorbing state C to A by going two steps, one to B and then one to A. And since it satisfies the definition, P is a transition matrix for an absorbing Markov chain. Now let's look at the diagram for Q. From A you can only go to C. So down here A only goes to C with 100% probability. B only goes to B, so notice B is out here by itself, just going to itself with 100% probability, and C only goes to A. Okay, so we know B is an absorbing state because you can only go back to B. So the first condition is met. But these two non-absorbing states, there's no way that I can go from A to the absorbing state B or C to the absorbing state B. So therefore P is not the transition matrix for an absorbing Markov chain. Okay, you can freeze the video and look at this. Here I'm just showing you that there's different ways to write the transition matrices for a diagram. And if you look at this diagram and then go down here and look at the transition matrices, you'll see that each of these transition matrices describes the paths in a correct fashion, but there's multiple ways that those paths can be described using transition matrices. Now, in matrices N and P, all the absorbing states precede the non-absorbing states. Transition matrices written in this form are said to be in standard form. So in other words, here we've got the absorbing states first, and then the non-absorbing states are below them. Same thing here. We have the absorbing states first, except I think I wrote that wrong. That should be backwards. I just didn't change it. But anyway, the point is those two, you actually have the absorbing states written in the first rows. So what is a standard form for absorbing Markov chains? A transition matrix for an absorbing Markov chain is in standard forms if the rows and columns are labeled so that all the absorbing states precede all non-absorbing states. And there's multiple ways to write this. So basically what's going to happen is you're going to have an identity matrix here in the top left-hand corner, and then you're going to have zeros in the top right-hand corner, and then you're going to have a matrix we'll call R here, and a matrix called Q here. Okay, so for example, this is in standard form. So notice here we have a 2 by 2 identity matrix. Here we have a 2 by 2 zero matrix. And here we can call this matrix R, and we can call this matrix Q. Okay, and over here I wrote the submatrices for you. And notice that the states in the row, these two states, come before these non-absorbing states, and also in the columns they come before these non-absorbing states here. So therefore we have the non-absorbing states listed first. We can now discuss the long-run behavior of absorbing Markov chains. Okay, if you read this, might freeze the video and read this problem first, but basically we've got state A, we've got state B, and we've got state C. So A would mean that we sell to A, B means we sell to C, and C would mean we do not sell. Okay, so if we look at A, we see that 20% of the estate owners choose to sell to company A. So 20% choose to sell to company A. So 20% goes to A. And then 30% choose to sell to company B. So 30% goes to B. And then 50% goes back to C. They do not sell. Now, the rest, these guys, A and B, they keep their land. So B keeps their 100% of their land, A keeps 100% of their land, but the C people, as I said, sell 20% to A, they sell 30% to B, and then they keep 50%. So if we put that in a transition matrix, A to A is 100%, A to B and C are 0. B to B is 100%, and B to A and B to C is 0. And then C to A is 0.2, C to B is 0.3, and C to C is 0.5. And this is an absorbing matrix because it satisfies the two conditions we talked about earlier. Now part C says if neither company owns any estates in the beginning, estimate the percentage of estates that each company will purchase in the long run. Okay, so we're going to grab our calculator. So basically at the beginning, no companies own the estates. So C has 100% of them. Okay, so now if we take that transition matrix and multiply it by this initial state matrix, we get this. Then if we take that matrix and multiply it by we multiply it again by that, we get this. And then if we multiply it again, we get this. So anyway, if you continue doing this, if you grab your calculator and to get s to the 9th, you take s to the 8th and multiply it times p, you get this. And so this appears to be converging to the values 0.4, 0.6, and 0. So in the long run, we estimate 40% will go to company A. I left out the A there, and 60% to company B. So eventually all will be sold. And then D says, suppose company A buys 50% of the estates before company B enters the process. Estimate the percentage of estates. Well, in that case, our initial state matrix would be 50% for A and 50% for C. So then if we multiply that times the matrix, we get this. And then if we multiply this times P, we get this, and so on. And so if you continue doing that in the long run, you'll get about 0.7 for A, 0.3 for B, and about 0 for C. So in the long run, we estimate 70% go to company A and 30% go to company B. And eventually all estates will be sold. I'm going to go ahead and do a couple more examples on the next one, but make sure you put the letter A here for company A in both spots to correct that. Talk to you later.